f of s and t is 2e to the s minus 3t plus s squared minus 4t, use the linear approximation of f of st at the point 3, 1 to estimate f of 3.1, 1.1. All right. Now, of course, one thing that we should note here is it's using the symbols s and t. Does that bother us that it's s and t and not x and y? No. A little bit? Okay. All right. Well, let me just let you know, you shouldn't be bothered. It's okay. They're symbols, and you can use whatever symbols you want. Now, there's a couple of key words. Of course, there's the word estimate. Well, that's good. It means you don't have to get the right answer. We just have to get an approximate answer. But how do we get that approximate answer? And they actually gave the game away. They have this word, linear approximation. I guess that's 2 words. Well, when you see the word linear approximation, what does that mean? What is the linear approximation? Oh, okay. Maybe it doesn't give it away. Okay, linear approximation. Well, it's kind of early in the day to do this, but okay. So, what is another name for the linear approximation? What? T? T? I heard a T.
L.
L?
Tangent plane.
Tangent plane. Okay, yeah. There were a few people who were whispering that. But, you know, it's fun to play. You guys are pretty good. You're pretty good. All right. So linear approximation is code for tangent plane. Now, why do we call it a linear approximator? Well, there's 2 things. First off, tangent planes are flat. And that's because it's a plane. And a flat thing is also a linear thing. So whenever you hear the word linear, you should be thinking, oh, that's like my flat object. What's our flat object of choice? In multivariable calculus, our flat object of choice are planes. Now, so that's linear. Where's the word approximation come from? Well, the word approximation comes from, and the idea is that the tangent plane, this is locally like the function. What that means, if you were to zoom in and look closely at the surface, z equals f of s comma t, and were to also put right on top of that the tangent plane, when you're very close, I don't know, say 0.1 away, they're almost identical. So that's where the idea of approximation comes from. So the linear approximation is tangent plane. So now that we know that, the rest of this problem is actually not so bad. So we say, okay, step 1, we're going to find our tangent plane. If we need our tangent plane, what do we need to find? Partial derivatives. So recall that our tangent plane has the form z equals f of ab plus, since we're using s and t as our symbols, f sub s at ab times s minus a plus f sub t at ab times t minus b. That's our tangent plane. So we have to find these values, the function ab, f sub s at ab, and f sub t at ab. I guess I should say, maybe we should have found the value of the function before we find those derivatives. Okay, so let's do some work with derivatives over in the corner here. So we'll start by writing down the function, our function f of s comma t. That's 2e to the power s minus 3t plus s squared minus 4t. What would be f sub s of s comma t? Well, derivative of e to the power s minus 3t with respect to s. Yeah, it turns out it's the same thing. Now you use the chain rule. Of course, the derivative of e to something is e to something times the derivative of something. In this case, the derivative will be 1. Derivative of s squared with respect to s, 2s. Derivative of minus 4t with respect to s, 0, goes away. Then we do f sub t of s comma t. Well, the derivative of 2e to the power s minus 3t, right, negative 6 e to the s minus 3t. In this case, again, you do the chain rule, but now the derivative of the inside part, the s minus 3t, the derivative of that is negative 3. The derivative of s squared with respect to t, 0. Derivative of negative 4t with respect to t, minus 4. All right. Now, after you have those functions and those derivatives, you evaluate. And where do we evaluate? Well, we're told it's the approximation at the point 3, 1. So this is our a comma b, 3 comma 1. So f of 3 comma 1. Well, we're going to have 2 e to the 3 minus 3. That's e to the 0. Plus s squared, which is 9, minus 4 times 1, so minus 4. So 2 plus 9 minus 4, 7. F sub s at 3 comma 1. Well, again, it's 2e to the 0 plus 2 times 3, so that'll be plus 6, gives 8. And f sub t at 3 comma 1, negative 6 e to the 0 minus 4, which gives negative 10. All right. So there we go. We have now our information about our function and our partial derivatives at our point AB, so that our linear approximation becomes, well, f of AB, 7, plus 8, which is our f sub s, times s minus 3, because a is 3, minus 10 times t minus 1. Okay. So finally, we say, okay, this is our tangent plane, this is our linear approximation, so we get that f at 3.1 comma 1.1. The value of the function is approximately what would happen if we look at 3.1 comma 1.1 on the plane. So we're going to plug these points, or rather this pair of points, into our plane. So we get 7 plus 8 times 3.1 minus 3 minus 10 times 1.1 minus 1. Well, these aren't too hard to find. 3.1 minus 3, that's 0.1. 1.1 minus 1 is also 0.1. So you get 7 plus 0.8 minus 1. Because 10 times 0.1 is 1. Well, what does that turn out to be? 7 minus 1 is 6, plus 0.8 gives 6.8. So that's the approximate answer. That's our estimate. Is it correct? No, it's an estimate. It's going to be wrong. I mean, there's this e thing involved. E would never be such a nice number. But we don't always have to be correct. Oftentimes, it's good just to have a good estimate. So that's what we're kind of after today. So where are we going? Well, we're going to get better estimates. So in general, when we have our partial derivatives at a point, we can say the following, that f of xy is the following. It's our linear approximation, also known as our tangent plane, plus an error. So the error, that's how far off you are. How far away is the function from that tangent plane? Now, generally speaking, what's true is that when a and b are close to the xy that you're plugging in, the error is fairly small. In fact, you could say that the definition of differentiable says that as x and y gets closer to a and b, the error goes to 0. But nevertheless, we'd like to get a handle on things. So that's what we just said about differentiable. So the question is, can we make it smaller? How can we make our error smaller? All right. So now we get to go and have a Calc 2 flashback. Let's remember from Calc 2, Taylor polynomials. All right. I can already tell that people are excited. Like, the best part of Calc 2, Taylor polynomials. Now let's recall what Taylor polynomials say. Well, one thing you could say is that suppose I want to approximate the function f of x. This is, again, single variable because we're just recalling what we did in single variable. So one thing we could say is that f of x is f of a plus a huge error. In other words, just ignoring all the other things that the function says, just like, well, if I'm close to a, plug in a, that's close. And then we said, no. Use the tangent line. So f of x is f of a plus f prime of a times x minus a. So this part right here is the tangent line. Now notice what happened to our error. It became smaller. So that by using that tangent line, you're getting a better estimate. And essentially what we're saying is, by using information about the behavior of the function at a, not just its value, but its behavior, we can improve. And then Taylor polynomial said, hey, check this out. Go and work at one more derivative. And you can make your error get even smaller. So the idea of Taylor polynomials, it's really a beautiful idea. It says, hey, don't just use the value of the function, but use the behavior, and the behavior being what's happening to your derivatives. You look at your first derivative and you look at your second derivative. Now you might be saying, hey, could we go further? The answer is, of course you can. You can look at many derivatives. But we'll start with the second. So, all right. So, our idea. Well, what's happening? Where do these terms come from? Now, one thing you can think of happening is that what you want to do is you want to have this right-hand side match the behavior at a. So you notice that for this first linear approximation, the tangent line, what's happening is you match the value of the function, but you also match the value of the derivative of the function. And if you look at the second order Taylor polynomial, this bottom line, you're going to match the value of the function, you're going to match the derivative of the function, and it's also set up to match the second derivative. Now, why is there a 2? Well, think about what happens when you take two derivatives. The first term goes away after one derivative, the second goes away after the second derivative, and then on this part, the 2 will come down. That's why you have to have a 2 there to cancel. Then the 1 will come down. So after two derivatives, the x minus a squared becomes just simply 1, and you've canceled off the 2, and so you're left with f double prime of a. So the goal then is to say, okay, if I want to mimic the function, let me match the derivatives. And if I can match the derivatives, I'm going to have a really reasonable approximation. So that's what we're going to do now with second order Taylor polynomials for multivariable functions. All right, here we go. Now, we'll start with the 0th order. So we can say f of xy is about f of ab. Okay, that's like what we had there. That's great. Then, of course, we can add a few more terms. And then we have the first order terms. So f sub x at ab times x minus a, f sub y at ab times y minus b. So now, if we throw these terms in, what do we have? Well, we have a function on the right-hand side which matches the partial derivatives, the first order partial derivatives. The second order says, hey, toss in all the second order derivatives. So you get 1/2 f sub xx at ab times x minus a squared plus f xy at ab times x minus a y minus b, and plus 1/2 f yy at ab times y minus b squared. Now, philosophically, it makes sense. We're saying let's match our derivatives up through order 2. How does it work in practice? Well, the same 2 that showed up when we're doing single variable shows up again in the f sub xx and f sub yy. And the reason you'll need the 2 is that the 2 will come down. Now you might say, well, wait a second, why isn't there a half here in front of this fxy term? Well, if you look at the exponents, you can see that it's intuitive that there shouldn't be a 2 because there's a 1 and a 1. So when you take the derivative with respect to x, a 1 comes down. Take the derivative with respect to y, a 1 comes down. So you're not really needing to cancel anything. An alternative way to think about it is you could say, well, maybe there is a half there, but remember that there's two mixed derivatives. There's fxy and there's fyx. In other words, you switch the order they take derivatives, but they're the same. And so if you were to combine them together, you'd get fxy. We're actually going to exploit that a little later on. The comment at the bottom just says that, this idea of Taylor polynomials is not really new. It's just saying, hey, let's build off of what we've already done. So tangent lines are actually Taylor polynomials. Tangent planes are actually Taylor polynomials. And what we're doing is we're just saying, oh, those are like really sort of base cases, and we're building off of these ideas. All right, so that's sort of the big idea for today. Now, examples. Lots of examples. All right. Find the second order Taylor polynomial for f of xy equals 2 e to the x plus y minus sine of x times y. All right. Well, what do we do? Well, what we need to do is we need to find all of our partial derivatives and evaluate them at 0, 0. That's going to be our building blocks. So we're going to just patiently work our way through our derivatives. So oftentimes, questions of this form are really aimed at saying, okay, do you know how to take your partial derivatives, and can you be patient? So f sub x, well, 2 e to the x plus y, derivative of sine is cosine, so that'll be minus cosine xy. And then it's like, oh, the chain rule, and so derivative of x times y with respect to x is y. Similarly, f sub y at xy is also 2 e to the x plus y, then minus cosine of xy times x. f xx at xy. So hopefully this is not too surprising. It may not be very exciting. It's just a matter of being patient. Sine of xy times y squared, because the derivative of cosine is negative sine, minus minus makes a plus. And then there's another y that comes out. Then fyy, I'll skip ahead one, because that one's not too bad. 2e to the x plus y, plus sine of xy times x squared, and of course, sort of the more interesting fxy. Well, do we want to take the derivative of x and then take the derivative of that with respect to y, or should we take the derivative first with y and then take that with respect to x? It won't matter in the end, and sometimes it's a little bit easier to do one than the other. In this case, they're so similar, it doesn't matter. So let's work with the f sub x and take that derivative with respect to y. So we get 2 e to the x plus y from the first term. From the second term, we're going to have to use a product rule, because there's a y and another y. So the derivative of the first term, that'll give us plus sine of xy. Then we have to take the derivative of the inside with respect to y, which will bring out an x, so there's an xy. And then there's going to be a minus cosine xy times the derivative of y with respect to y, which is 1. All right, so that's the first step. When you're looking for a second order polynomial, you've put in lots and lots of derivatives. All the derivatives up through order 2. So step 1, take your derivatives. Lots of them. What happens after you take your derivatives? What do you need to do? You need to evaluate. Where do you evaluate? At wherever they tell you. In our case, it's at 0, 0. So we start plugging in. F at 0, 0. What do you get when you plug in 0, 0? You get 2. How about f sub x at 0, 0? What do you get there? 2. F sub y at 0, 0. What? 2. Okay, I see a pattern going. But sooner or later, we're going to break it. fx at 0, 0. 2. Oh, maybe we won't break it. All right. The thing is that, 0 is really hard to overcome because y is 0, x is 0, sine of x, y is 0. If we skip to the bottom here, fyy at 0, 0 is also 2. How about fxy? What is that? It's 1 because you get 2 plus 0 minus 1. Okay, well, at least something broke the pattern. Okay, so now what's the answer? Well, in general, it's going to be f0, 0, if we're at 0, 0, plus fx at 0, 0 times x minus 0, which is just x, plus fy at 0, 0 times y minus 0, so that's y, plus 1/2 fxx at 0, 0 times x squared, plus, I don't know if I'll make it, but okay, we'll get close. We'll get close. Plus fxy at 0, 0 times xy, and then plus 1/2 fyy at 0, 0 times y squared. All right. So that's the second order Taylor polynomial at 0, 0. And we just plug in the values. So you'll get 2 plus 2 times x plus 2 times y plus 1/2 times 2 makes x squared plus 1 times xy, which makes x times y, plus 1/2 times 2, which makes y squared. So that is the second order Taylor polynomial. There you go. So again, the process is not so bad. You can write it down in a couple of steps. You might as well for reference. So step 1, take your derivatives, all derivatives up through order 2. And you need those for reference. Step 2 is evaluate at your point. And step 3, of course, is put it together. And that's it. That's not so bad. That's not so bad. We can do it again. So, suppose you want to find the second order Taylor polynomial for f of xy equals x squared e to the y at the point 1, 0. Now notice, this is at 1. So you don't always have to do things at 0, 0. You can do it anywhere you like. So keep that in mind. Now this one is not so bad to do. I hope. Let's find out. But again, the process is the same. So let's see, we'll write f, that's x squared e to the y. F sub x, what's that? 2x e to the y. F sub y, x squared e to the y. So remember f sub y, you go back to f. F x x 2 e to the y. F x y 2x e to the y. Because you can come up to f sub x and take that derivative with respect to e to the y. The 2x to be a constant, derivative of e to the y is e to the y. Or you could go to f sub y, take that with respect to x. You get the x squared, derivative of that's 2x, and e to the y stays as it is. F y y. X squared e to the y. Okay, so that's a little bit easier to write down those derivatives. Now you evaluate f at 1, 0. 1. F sub x at 1, 0. F sub y at 1, 0. 1. F sub xx at 1, 0. 2. F sub xy at 1, 0. F sub yy at 1, 0. 1. All right. So now what do we get? Well, it's our function at our point, so that's 1, f sub 1, 0, plus f sub x 1, 0, which is 2. And what do I multiply this by? This is fx at 1, 0 times x minus 1. Remember, it's x minus your point. And here it was 0, 0, so we could have just x minus 0 or just x. Okay, plus f sub y at 1, 0, so that's plus 1, times what? Y. It's really y minus 0. All right. Now, f sub x at 1, 0 is 2. But remember when we go into our second order, we have to maybe divide. The fxx has this over 2 term. So fxx over 2 will be 1. And I multiply that by x minus 1 squared. fxy, you don't need an extra half. Just leave it as is. What do we multiply that by? X minus 1 and y. And finally, the fyy, again, there's a half. So 1 times a half is a half, and y squared. And there you go. Woo! Good. Good. All right. Phew. All right. Well, what do we do? So why do we want this? Well, the answer actually comes back to where we started. It says, hey, we can get better approximations. So instead of using first order, we can go to second order and say the second order should be a better approximation than the first order was. So let's put that to the test. Now, okay. Do you want to do this again, or should we try to do it a faster way? Now, I should warn you, you should only attempt this if you're a trained professional. Now, we're hoping that you're going to get to that level, but there's actually some things that you can do to sort of speed things up. For instance, notice that you have e to the y. So my function is 3x e to the y plus 2y e to the x minus 4xy. Okay, so far no big surprises. But what do we know about e to the y? Well, now let's test your recall. Do we know the Taylor polynomial for e to the y? This probably will end up not being faster, but it starts off as 1 plus, do you remember the next term? Y, because we're e to the y, plus, do you know the next term? 1 half y squared, and dot, dot, dot. Then you have the 2y e to the x, similar, but with x. It's 1 plus x plus a half x squared plus dot, dot, dot. Then minus 4xy. So essentially what I'm saying here is we did this kind of stuff before in Calc 2 where we said, hey, I can rewrite e to the x as this Taylor series, or e to the y as this Taylor series. And Taylor series is just a fun way of saying it's a big polynomial. All right. So if we were to now expand this, well, what would we have? Well, we'd have the 3x. And then we'd have the 3xy. And then we'd have this term, 3 halves xy squared. Now, here's the question. Do I care about that term? And why not? Okay, so let's go through those two questions. Do I care about that term? No, that's the correct answer. Why not? We're doing second order. Xy squared, how many things do we see? An x and 2 y's. If we add that up, that's 3. So those will only show up when you get to third order. So those are gone as far as second order is concerned. So we only want to keep things which have at most 2 terms. They can be 2 x's, or just 1 x, or maybe an x and a y. But once you get past 2, it's not going to be around once you get to the second order Taylor polynomial. Okay, for the next part, where do we get? We get the 2y. We get the 2xy. And then we get a bigger term, which we're not going to worry about. Do I care about the 4xy? Yeah, I do. 4xy, and then plus, the other stuff is what we call higher order terms. Whoops, I can spell higher. Higher order, nope, I can't spell. Never mind. Higher, abbreviate order as ORD terms. All right, higher order terms. Those are terms which are essentially, from the polynomial perspective, degree 3 or above. This first part right here, this is a second order Taylor polynomial. But we can clean it up a little bit. What's something we can do? We can combine some like terms. So we get the 3x plus 2y, and the rest of them combine to give us xy. Now, if you don't believe that this works, you can try it the other way. Take all your partial derivatives, and you'll get to this point. I promise you, you will. If you're not comfortable doing this, don't do it. Because you're going to end up with the same answer. And you should do what you're comfortable with, as long as it's correct. You might say, I'm really comfortable with writing down 7 as the answer to every problem. You shouldn't do that. But anything that's correct, go ahead and keep doing that. All right, so what does that tell us? Well, this right here, this is an approximation for f of xy near 0, 0. So we can say that f of 0.1, 0.2 is approximately 3 times 0.1 plus 2 times 0.2 plus 0.1 times 0.2. Well, that's 0.3 plus 0.4 plus 0.1 times 0.2? 0.02. And if you put that all together, we get 0.72. There we go. And that's an approximation. Now you might say, well, how does that compare to if we had just used a tangent plane? And the answer is, what's the difference? Well, the tangent plane wouldn't have that xy term. So by going through all these second derivatives, we went from 0.7 to 0.72. So that was what the second derivative gave us, the 0.2. And they might say, what did the first derivative give us? The answer is the 0.7. Because if you just plug in 0, 0 into the function, you get 0. So 0 was our 0th order approximation, 0.7 our first order, 0.72 our second order. And you'll discover that 0.72 is closer than 0.7 and is definitely a lot closer than 0. Now, could you get better? Yes. But hold on, that's the end. Let's not get ahead of ourselves. All right, a different kind of question. So now, they're going to give us the second order Taylor polynomial and say, hey, look at it. Here it is. We don't even have to do anything. And we want to get information about the function. So we have this function, this f of xy. This is a second order Taylor polynomial. This is the Taylor polynomial here. 3 plus 2x minus y plus 2x squared plus xy minus 4y squared. And that is the second order Taylor polynomial at 0, 0. So part A, we want to find derivatives for f, x, y at 0, 0. And the question is, can we do it? Well, what do we have? If we look at our g of xy, so that's 3 plus 2x minus y plus 2x squared plus xy minus 4y squared. Remember, this is our Taylor polynomial. Now, in terms of our Taylor polynomial, what would the 3 correspond to? That would correspond to f at 0, 0, because that's our constant term. How about the 2x? Well, what does the 2 correspond to? Well, that would be fx at 0, 0, Because remember, it's your partial derivative with respect to x at your point times x. How about the minus y? Well, really, you should think of this as a plus negative 1 times y. The negative 1, what is that? Fy at 0, 0. Now we come to the 2x squared. What does the 2 correspond to? Is it fxx? Yeah, remember that this coefficient was 1/2 fxx at 0, 0. Okay, now this plus xy is really plus 1 times xy. What does the 1 correspond with? Is it fxy at 0, 0? It is fxy at 0, 0. Yeah. Okay, good. Finally, this negative 4, which is really is plus negative 4. What does the negative 4 correspond to? Half fyy at 0, 0. So if we have the second order Taylor polynomial, what we really have is stored information about derivatives. That's what a Taylor polynomial does, is it stores information about derivatives. So we have, for this one, f at 0, 0, we'll just write it down as a nice column here. That's equal to 3. Fx at 0, 0 equals 2. Fy at 0, 0 equals negative 1. Fxx at 0, 0 is 4. Fxy at 0, 0 is 1. And Fyy at 0, 0 is negative 8. Okay, so that's the answer for part A. Now it says there's a part B. Let's see what part B says. It says, hey, you know what? It turns out that this is now not the Taylor polynomial at 0, 0. This is a Taylor polynomial at 1, 1. Let's find the derivatives now for the function at 1, 1. And can we do it? Now I just said that the Taylor polynomial stores the derivatives. All right. So, how do we find f at 1, 1? Will it be 3?
Yes.
Not necessarily. What? Okay, so think about our Taylor polynomial at 1, 1. What would it look like? Well, it would look like f at 1, 1. You're like, yeah, see, exactly, 3, right? Plus, the next term would be fx at 1, 1 times what? X minus 1. Plus fy at 1, 1 times y minus 1. And fxx at 1, 1 over 2 times x minus 1 squared, plus, because I ran out of space, dot, dot, dot. Now, notice someone has come along and said, oh, my algebra teacher said you should always expand and simplify. So they didn't leave it as x minus 1. They multiplied it out, and then they gathered like terms together. And now we're like, no! You've made it harder on us because we can't read off the answers anymore. Can we get the answers? Yes, we can. We still can get the answers, but we can't just read it off because it's not in the right format. We don't have things like x minus 1, y minus 1, or x minus 1 squared. So the question is, how do we get the answers? And the way we do it is to say the derivatives still have to match. That's what a polynomial does. When it's a Taylor polynomial, the derivatives have to match. So what we do is we just make a very simple observation. If the derivatives have to match, that says that f at 1, 1, that has to be g at 1, 1. F sub x at 1, 1, that has to be g sub x at 1, 1. And we're going to do this all the way down. So what we do is we go through and we say, let's just sort of do a Taylor polynomial for that function. Because the Taylor polynomial for that function has to match the Taylor polynomial for the original function. So that's our game plan. And that's how we can recover the information. All right. Well, where to begin? Well, we're going to be doing a lot of, hopefully we have enough space. Okay. Probably not, but We'll try our best. All right. We know what g of xy is, so let's just plug in 1, 1. When we plug in 1, 1, we get 3 plus 2 minus 1. We should probably, okay, how about, let's start over. 3 plus 2 more makes 5, minus 1 makes 4, plus 2 makes 6, plus 1 makes 7, minus 4 makes 3. Oh, it turned out it was 3. Didn't have to be. Okay, but good thing we checked. All right, now, for the rest of it, we have to take derivatives. Okay, whoop, we're almost off the screen there. Okay, g sub x, what does that turn out to be? Start off, the derivative of 3 is 0, the derivative of 2x is 2, the derivative of minus y is 0, 2x squared becomes 4x, xy becomes y, minus 4y squared goes away. G sub y, well, negative 1. And then we come here, that'll be plus x and minus 8y. Gxx, that'll be 4. Gxy, 1. And gyy, negative 8. So, well, some of these are pretty easy to find out. Gxx, 4. Gxy, 1. Gyy, negative 8. Okay, that leaves us gx at 1, 1 and gy at 1, 1. Plug in 1, 1 into g sub x. 2 plus 6 plus 1 gives, 2 plus 4 gives 6, plus 1 gives 7. Gy minus 1 plus 1 is 0, minus 8 gives minus 8. And therefore, this is the information. If the g of xy was the Taylor polynomial at 1, 1, this would be the partial derivatives of the function at 1, 1. Again, the moral is, the idea is, the second order Taylor polynomial matches derivatives of the function up through second order. Now, why do we care about these things? Well, we care about them because they're going to help us do something in our next session. But to understand that, we have to talk about something called quadratic form. And I'm going to tell you right now that for the next about 3 or 4 minutes, what we talk about, if you don't get it, it's not the end of the world. This is about matrices, and there's a wonderful class that you get the opportunity to take, possibly, called linear algebra. So if this is like, man, this sounds super weird, it's okay, don't worry about it. Just relax and enjoy the math. Let the math flow through you and like, wow, beautiful. Okay, so suppose we let delta x be x minus a and delta y equal y minus b. So the change in x and the change in y. Then what we can do is we can write our second order Taylor polynomial. If we just look at the second order terms, you get the 1/2 fxx at ab delta x squared plus fxy at ab delta x delta y, 1/2 fyy ab at delta y squared. Now here's the really cool thing. If you've done matrices before, it turns out you can write this as a sort of a matrix form expression. So namely 1/2, then you have this vector. And the vector is the set delta x delta y. Then you have this matrix in the middle, which consists of all the second order partial derivatives. All right, cool. So, what do we have? Now, it turns out that when the gradient of f is 0, so that means that your f sub x is 0 and your f sub y is 0, then if I want to understand what the function is doing, I push into the second order derivatives. So essentially, if the first derivatives are 0, the second derivatives are giving the behavior. So that says that when gradient of f equals 0, and we'll talk about why that's interesting, this is telling us our behavior. So we'd really like to understand, how do we interpret this? And here's the linear algebra part. If you have a matrix, 2 by 2 matrix, so A, B, B, C, you'll notice that these entries here are meant to be the same. And you notice that fxy is the same as fyx. So that's the kind of number we have, kind of matrix we have. So if we have this special type of matrix, there are two numbers. We denote them with the Greek letter lambda. Lambda 1, lambda 2. They're called eigenvalues. Eigen, German, means the same. Now it doesn't mean lambda 1 and lambda 2 are the same, but rather that these values have some sort of repetitive sameness about them with respect to the matrix. And what's really cool about these is that this matrix, it turns out you can write it as lambda 1 times a square term involving the delta x, delta y, and lambda 2 times, again, another square term involving delta x and delta y. The alpha, beta, gamma, delta, that's a little bit technical. In terms of matrices, these are called the coefficients for the eigenvectors. Again, you don't need to worry about it. The important thing is that any 2 by 2 matrix that has this format can be written as this combination of these two terms. Now what we want to sort of say is, okay, what does it look like? So we're going to talk about that. Suppose lambda 1 and lambda 2 were both positive. So what's happening? Well, the cool thing about squaring is you're going to be greater than or equal to 0. So if we square things, that says, oh, no matter how delta x and delta y move, I'm always going up. So that says we look like something that looks like this, a bowl. So that's if they're both positive. Now, that's not the only possibility. What if they're both negative? Well, if they're both negative, you have a negative times this term and a negative times that term. That says no matter what I do, when I perturb things, I'm going to go more negative. So we're going to go down. So that means our shape looks like this. It's an upside down bowl. What's another possibility? Someone's seen ahead. Well, another possibility is that one of them is positive, and one of them is negative. Now, what does that mean? Well, that means it might be the case that in one direction, we're going up. But if we go in a different direction, we're going down, because lambda 1 could be positive, lambda 2 could be negative. So that has the shape, someone already noted, that's called the saddle. And it looks something vaguely like this. So that in one direction, it looks like, oh, I go up. So if this is our point, as we move in one direction, we're going up. But in another direction, if we move, we'd go down. So that's the saddle. Now, the last thing is, at least one is 0. And what does that look like? The answer is, we don't know. There's not enough information. Okay, so what's the good news? Well, it turns out that if we have this 2 by 2 matrix, that lambda 1 times lambda 2 is equal to AC minus B squared. So if AC minus B squared is positive, they both have the same sign. If AC minus B squared is negative, they both have different signs. And if it turns out that we get 0, then one of them is 0. All right, and now to finish up, you might say, this is all well and good, and I like second order, but can we go further? The answer is yes. There's two things you could do. You could look at a second order Taylor polynomial for x, y, and z, and then you have your 0th, first, and your second order terms. You can see there's a little bit more. Or you can say, no, I want third order. Can you do that? Yes. 0, first, second, or third for f, x, y. So, can you go even further? Absolutely. Now, will you? No. We don't expect you to go further than second order, but we want you to know it does exist, and we'll pick up again next time.